Before we begin, there will be images of real blood splatter, so viewer responsibility is advised. Thank you! Can we use mathematics to prove blood splatter? Forensic scientists and blood analysis technicians have tried to rationalize the unpredictableness of blood using trigonometry, so let's get started on one of their most famous techniques. Let's say an individual was sitting at their kitchen table. A robber comes in and shoots the individual, spewing blood all over the floor. Now, we're asked to find the angle at which the blood struck the floor. The most common route to take when finding the angle is to use trigonometry. Throughout this video, you will hear me mention this angle as the impact angle. In this scenario, let's assume that the blood drop is spherical in the air. Using this assumption, we can draw two parallel lines that intersect with the ground to represent the projected plane when the blood drop will hit the ground. Drawing a perpendicular line from the intersection of the ground and the bottom line to the top line allows us to claim this as a right angle. As I've mentioned before, the parallel lines represent the cross sections of the blood stain. For there to even be parallel lines, we must assume that the cross section of the blood drop in the air is the same as the stain after impact. Since we are calling this the right angle, the length of the blood drop is the hypotenuse, and the width of the blood drop is the opposite side of the angle. From here, we can use inverse of sine to find the angle of theta, our impact angle. For demonstration purposes, let's say that the width is 5 millimeters and the length is 7 millimeters. The inverse of sine of 5 divided by 7 is between 45 and 46 degrees. This is considered our impact angle. Simple enough, right? Wrong. Several of the assumptions I and other technicians have made are false or produce a significant risk of error. The first assumption I made is that we can assume the blood drop is spherical in the air. When the blood droplet leaves its source, it almost immediately forms a spherical shape. This is due to the fluid dynamics of falling blood. The surface tension of the droplet is what keeps the spherical shape while traveling through the air. This assumption is extremely close to accuracy, so it is unlikely that this is what is causing our error. The second assumption I made is that to draw the parallel lines, the cross-section of the spherical shape in the air is the same as the stain left on the surface. Even though this seems to make sense initially, if we experiment with cross-sectionality, we see that this is not true. If we cut a sphere with a single, straight, diagonal line, we will never produce an oval or elliptical shape. Using this logic, we will never be able to produce the same shaped cross-section as seen in the stain. Even more, we should realize that a blood droplet is a 3D object and a stain is a 2D object. Why is this important? Due to the conservation of volume, a 2D stain will not represent the total volume of the original drop, and we cannot assume that the stain represents the entirety of the blood drop. This will mess with our measurements of length and width, decreasing the accuracy of our trigonometry calculations. An assumption that I didn't directly state, but was implied, is that the blood drop was of average uniformity. This means that we assume the mass to be equivalent to the average drop. This is highly unrealistic because of the numerous conditions and factors that play into red blood cell ratios, such as anemia, drug addiction, children, the elderly, aborted fetuses, malnourished, homeless, and those who suffer from heart attacks. Even if we found that this individual did not experience any of these in their lifetime, it is important to note that the red blood cell count ratios are not the same for every organ in the body. Too many differentiating factors play a role in the mass of a blood drop to assume constant uniformity. This is crucial because different masses can react differently to surfaces and alter what we assume is the normal reaction of a blood drop. Similarly, we do not have enough evidence of the blood's relationship with different surfaces such as wood, carpet, glass, and other materials where blood can strike. So even after all of these assumptions and known complications, why do some scientists continue to use this practice? To start, many use these calculations as a guide or estimate, especially when they have nothing else to work with. Impact angle calculations are generally considered to be accurate within 5 and 7 degrees depending on the scenario. Stains that are circular shaped have proven to show a greater error level. When looking at stains between 10 and 45 degrees, we find that the error rate is only between 2 and 3 degrees. For stains of 60 degrees, the error increases to about 6 or 7 degrees. Anything higher than 60 degrees suggests a significant amount of error. Analysts probably continue to use this practice also because it seems to work in controlled experimentation. In these mock scenes, the weapon is usually one of blunt force impact rather than a firearm. The velocity of both of these scenarios varies greatly and may be the source of issues as to why the controlled experiments lead to a better outcome. Finally, one major assumption is made when analysts use trigonometry and geometry to find the impact angle. They assume that the droplets face straight line trajectories, or in other words, stay at the same angle from the start of the path to reaching the final surface of impact. It is a common misconception that blood falls in a stereotypical parabolic arc, but in reality, especially in high-velocity splatters, starts with a constant angle and finds a greater slope. This is due to air resistance and gravity affecting the droplet. So, if their theories don't work, what can we try instead? Unfortunately, the answer isn't exactly clear. As humans, we try to rationalize and predict nature and concepts around us that aren't always necessarily predictable. Blood, for instance, is a unique substance itself, but becomes much more complicated when factoring different traumas that cause blood, weapons used, the environment, blood density, and so many other components that alter what we want to assume. After completing this research, it has come to my attention that the best way to figure out forensic science applications is through experimentation. Once analysts grasp a hold of their estimates, they can take those to a lab or mock observation to give their best and what they believe to be the most accurate conclusions. In summary, while we might efficiently estimate forensic calculations, such as angles, it is nearly impossible, as of now anyway, to precisely measure blood pattern analysis using mathematics. Thank you for watching!